So yesterday we were doing a few concepts on simply connected regions and multiply connected regions, and also we were doing Cauchy's integral theorem, an extension of Cauchy's integral theorem to the multiply connected regions. Okay, so yesterday I already explained you in the previous lecture that what are simply connected region. For example, this is a simply connected region where every closed curve, you make any sort of closed curve, any closed curve in this particular region would always converge in this particular region itself. Okay, so if you try to shrink this region, it will always converge in this particular region. Okay, but what about multiply connected region? So for example, this is a multiply connected region because see, here you take any closed curve. Let's say this is your closed curve, this is your closed curve, this is your closed curve. No doubt, it converges in the angular region. But what if you take a closed curve in this fashion? This is also a closed curve. Now, when you shrink this curve, it will go inside this circle that is mod z less than a. In fact, you can see that this region, which I have shaded in black, can be written as mod z less than b and mod z greater than a. Okay. So in this regard, I would say that this is a multiply connected region. So what is a multiply connected region? Multiply connected region is a region where every closed curve in this region, when shrunk, goes out of the region. So for example, if I'm saying my R2 is a multiply connected region, then if R2 is a multiply connected region, then any of the closed curve that I make, will go in every closed curve, not necessarily lies inside the region. For example, again, I'll tell you, let's say, for example, if you take this curve, I have no issues. Okay. But if I take this curve, this is a closed curve. Let's say this is my closed curve. And if I try to shrink this curve, I will go inside the region that is mod z less than a. So if I try to shrink this curve, which I'm representing in blue, I will go inside a region that is mod z less than a. And clearly, mod z less than a is not there in this region. Okay, so clearly, an annular region, it accounts for something called as multiply connected regions. So this is a multiply connected region. Okay. Incidentally, we derived a theorem yesterday that's called as Cauchy's integral theorem, which says that integration fz dz over closed curve C, and this particular closed curve C lies inside a simply connected region. So if my closed curve C lies inside a simply connected region, then I would say this integral is 0. Okay, so this we derived yesterday. You can see the lecture from yesterday's lecture, and you'll find that it's reasonably easy to prove this. Okay, so integration fz dz over this contour closed curve C with a curve that particular curve C lies inside a simply connected region, and this particular thing comes out to be 0. Okay, now the question naturally arises as to what will be the generalization when this simply connected region goes this particular Cauchy's integral theorem is to be extended to multiply connected region. So what if I have to extend the same theorem, that is Cauchy's integral theorem, to multiply connected region? Okay, and eventually you'll find this multiply connected region. This will be very helpful. Okay, so let us see how would you do that. So yesterday I was doing this. I'll do it all over again today also. So let's say I'm making a curve C. And let's say I'm traversing counterclockwise. And let's say if I have some closed curves here, let's say C1, C2, let's say C3, and then let's say C4. So yesterday I told you this is this region I'm talking about. This particular region clearly is a multiply connected region. Okay, so it is a multiply connected region. Why? Because not every closed curve inside this region would converge in this region. So for example, if I make some region around this particular C3, and if I try to shrink this region, I will get into C3, and any point inside C3 does not lie in the black side region. So you can take this region, this region which I'm shading in red is your multiply connected region. Yes or no? So this is your multiply connected region. So I'm shading it in red. So this is your multiply connected region. Okay, so how to go about all these things, like other regions which are not in red. So for example, now this red region is your multiplicated region. Okay. So what would you do? Okay, so this is a multiplicated region. Why it is a multiplicated region? Because not every curve which I draw will remain in the red region only. Because it may be possible that if you make some curves around, let's say, I just mark this in yellow. So let's say this is, or some other color, darker color, so that you'll be able to understand what I'm trying to make the point. So let's say this is, these blue regions are not in the red ends. Okay, so you understand my point. Now, you make any curve in this particular region, you will remain in this particular region. Let's say I make a closed curve here, and if I shrink it, I will remain in this region. But what if I make a curve here? And if I try to shrink it, I will get into the blue region, and that suggests me that this is not a simply connected. So how to extend this Cauchy's integral theorem, which is applicable for the simply connected region to a multiply connected region? Yesterday I told you that for mathematical convenience, what we'll do, it's just a matter of mathematical convenience, that we'll do something called as cut lines. So basically what we'll do some slit kind of construction. The slit kind of construction would allow me to make this entire thing, will allow me to transform this entire thing into a simply connected region. So what I would do is, I would simply make a cut around all these points. Let's say if I'm doing this way, I'll say just make a cut with epsilon tending to 0. So this cut is epsilon tends to 0. This is your C1. Again, I would make a slit, and this would be very narrow, as narrow as you may think. Okay, so this kind of cut region, when I'll make, what will happen after this slit? Let us see. Okay, so let us see. So if I'm integrating over C, like if I'm integrating over this region R, now these slits, understand these slits are very narrow. So these are very narrow. So the region R, which is which this red region, if I try to integrate, what will remain overall? So if I integrate my function fzdz over a closed curve C, which happens to be in the multiply connected region. So this is a multiply connected region. This I have drawn. This is a multiply connected region, and this multiply connected region, if there is a say, let's say, closed curve C which encloses, now what would be this integration? So I've already told you, by constructing the slit construction, what we are doing is, now if you try to make, like, if you go along this way, now you will enter this particular curve. You'll go around this, then again you'll come out of this, then you'll go this way, again you'll go this way, you'll come this way, you'll go this way, you'll go this way, you'll go this way, you'll go this way, you go this way, and I think this is clear to you. Okay, are you getting my point? So basically what is happening is, now in order to go up about this closed curve C, instead of saying that this is my multiply connected region, what I would do, I would simply make it a simply connected region. Once I've made it a simply connected region, this integration would become 0. Okay, because here there are no such singularities. Yes, also note that this, in this red region, I'm stating that my function fz is analytic. So if I'm stating that my function fz is analytic in this red region, then what would I say? I would say that my fzdz is equal to 0. Yes or no? Okay. Now, if my function is analytic, and if I have to integrate it, how would I do? So if this integration would be equals to what? This integration would be equals to what? I would say this integration would be equals to, oh no, sorry, this region R. So if I'll say that in region R, my function fz is analytic, then this particular integration can be replaced by this will be 0, but this particular integration can be replaced by integration C anti-clockwise. Then I would go on to say this. Let's say this is something like इसको मान लेते हैं m1 n1, and this will be n1 dash m1 dash. And yesterday I told you integration along this and integration along this would cancel out. So this I'm not writing. So it will be equals to plus, I think along C1, I would write clockwise. Then I would plus, I think there would be some terms like these terms will be there, n dash m dash plus integration m dash n dash. This will remain there. Okay, so this will be there. I'm not denying that. I'm saying this integration would be there. This integration would be there. And this integration gets cancelled with this integration, because yesterday I told you integral a to b fz dz is equals to minus integral b to a fz dz. So this integral would cancel out. Okay. So so this integral would cancel out. I'm not writing that. Then what will happen? Again, I will come back to this particular, let's say this is your m2, this is your n2, this is your n2 dash, this is your, let's say, m2 dash. Again, this will cancel out. This is your C2. Again, C2 traversing in the clockwise direction. So what would be the case? So what will happen is all these small curves that I'm drawing, C1, C2, C3, C4, it will be equals to summation I equal to 1 से लेकर 4 clockwise orientation integral fz dz over all the CIs. Okay. And obviously there will be two integrations. Those will be along some MIs and NIs plus integration MIs, NIs, and this will get cancelled. So I'm not bothered about it. I've already told you that my function is analytic in this region R, that is the multiplicative region R. So this integration is 0. And if I have to find an integral over a closed curve C, it is equal to finding an integral over this sort of construction. Okay. The only benefit is this region R was a multiply region. It has converted into a simply connected region, which gives me a freedom to use the Cauchy's integral theorem and to write this integral over R as 0 for this particular sort of construction where I have introduced cut lines for my convenience. Okay. Now further, as we see, this particular integration would come out as integral over closed curve C fz dz, which we were interested in finding out, is nothing but it is equals to minus integration of all these, minus integration along all these curves, closed curve, that is all these CIs, CIs FZDZ, and in clockwise sense and negative is there, so I will remove the negative. So this will also become anti-clockwise. So eventually what we'll find, instead of finding integral over this entire C, this integral would be equivalent to finding the integrals over these closed curve CIs. Are you getting my point? ये चीज समझ में आई? So this is how your Cauchy's integral theorem works in the multiply connected region. For very simplicity, I did the same thing for doubly connected region yesterday, and I was able to show you that this, let's say this is your C2, let's say this is your C1, and if I'm integrating over C2, it is equals to integral over C1. And I told you yesterday that these two, this particular doubly connected region R, here my function is analytic. So if my function is analytic, you should understand that there would be no such singularity like here. So what does it mean? It means that my integration would not change if I try to deform the contour into a different contour. Let's say if I'm not able to find an integration over C2, let's say it is difficult to find integral over C2, what I can do, I can continuously deform my C2 to C1, okay? Continuously deform my C2 to C1 and find the integration over C1, provided I am not encountering any singularity in that process of deformation. This is what is known as principle of deformation of contours. Okay, so this is what is called as principle of deformation of contours. So let us, yesterday I was doing an example. Let us again do it so that it becomes a revision for you today. So let me do an example for you. So the example was, I think, integral. You were supposed to find integral, I think, z square. Just give me a minute. Okay. Okay. So this was the integral. Integral was integration of this function which I'm writing right now. Okay, so this was the question. Integration, I think z dz upon 1 plus z square over curve C, over curve C, where C is the, I think, upper half of the semicircle given by mod z plus 1 by 2 is equal to 1 by 2. Okay, traversed anticlockwise. So again, I'm writing anticlockwise. Anticlockwise. Okay. So basically, what it would mean. So what it would mean is that we are integrating. We are integrating our function z dz z upon 1 plus z square over this upper half of the semicircle. Okay. So we are integrating over this upper half of the semicircle traverse clock anticlockwise. Okay. So this is my curve C, the upper half of the this upper, what I should say, upper semicircle, upper half मत कहो इसको upper semicircle. So upper semicircle मतलब ये curve. Okay. Okay, so this will be minus 1 by 2 comma 0 because see, you can clearly see that the center of the center of the this thing, I mean circle would be, or you can say semicircle would be minus 1 by 2 comma 0 and the radius would be 1 by 2. So here it would be in this fashion. This will be point minus 1 comma minus 1 comma 0. This will be your origin. I don't think there is an issue about it. Okay. Now, what does first understand my point that where does the singularities for this particular function lie? So the function which is mentioned in the integral, it is like 1 plus z is z upon 1 plus z square, and we have to find where the singularities lie. So singularities lie at points plus minus iota. So if my singularities are at plus minus iota, so I'll mention it. These are the singularities. Now understand my point. This particular, like if I just enclose this particular region, tell me, are there any singularities here? Bharat, are there any singularities here? The region that I'll mark like this way. No. Okay, so there are no singularities. Okay. Now, what does principle of deformation of contour tell me? It says that if at all, if at all I have no such singularities, what I can do, I can continuously transform, yeah, I can continuously deform my curve into a different curve. So let's say I can deform my curve and make it parallel to what? Make it parallel to what? This is your curve. So you have deformed the curve to this. So principle of deformation of contours agar lagayenge, then what will happen is this particular curve C will get deformed to this particular thing. Simply this. So instead of integrating over this curve C, which is very difficult to do, like right now it is very difficult to do because you'll have to do something like you'll have to take Z as some parametric coordinates. I think it would be, if I'm not wrong, it will be Z minus half is equal to rho e की power iota theta, and theta lies between pi to 0, or probably you will have to take are you getting my point? So let's say if I have to take the radius and all those stuff, I'm not interested in how to find this integral because otherwise I'll have to do all these things. If I have to find over this in, like if I have to find an integration over this, then I will have to write the uh, parametric equation to parametric coordinates to the circle or semicircle, and I have to integrate parametrically. Now, what is a freedom that I've got from principle of deformation of contours is that I will simply integrate over this region, in this line, instead of integrating over this, because I can, in principle, deform my contour C to this particular line since there is no such singularity. So I am not encountering any singularity. So I can, in principle, go on and continuously I can transform this, continuously I can deform this particular curve C to, let's say, this particular curve. You say, I don't know, how should I say, let's say this is your line L. Okay, so you can integrate over C or you can integrate over line L. This means one and the same thing. Because by principle of deformation of contours, you know that in I can go on deforming the contour provided I do not encounter any such singularity. Okay, so what will be the integration? So why I'm doing this? Because right now I have not taught you in detail how to integrate like parametrically. I've not done lot many questions, but you know from your standard 12 an integration where only x is involved. So basically, what does happen on x-axis? X-axis y coordinate is 0. So this entire thing will become x upon 1 plus x square dx. Okay, so this entire integral would be transformed into this integral from where to where? From 0 to -1. So the direction is 0 to -1. Sorry, -1. And if you integrate, you just multiply with 2, multiply half. So what you'll do, you'll get ln 1 plus x square from 0 to -1. And eventually you will end up getting, I think, 1 by 2 ln. So see how simple the life has become. So this is the beauty of principle of deformation of contours. Let us do another question, a very simple question, so to say, and try to understand. Okay, so if I do, let's say, if I do this question for you, okay, so I'm doing this. हाँ बेटा बोलो.
सर एज पर द थ्योरम अगर कोई भी सिंगुलैरिटी हमारी लाइन नहीं करेगी कंटोर के अंदर तो जीरो नहीं होना चाहिए रिजल्ट.
बट बेटा वो क्लोज्ड रीजन था. दिस इज नॉट क्लोज्ड.
एक्सिस को हम एक्स एक्सिस को क्लोज कंसिडर नहीं करते.
नहीं देखो, अगर तुम्हें वो लगाना है देन व्हाट यू कैन डू. लेट्स से तुम जो कह रहे हो वो तुम्हें लगाना है. सो लेट्स से व्हाट भरत सेज, अगर वो करना है, दैट विल आल्सो गिव एन आंसर. So what Bharat says is, Bharat says that why don't you use a Cauchy's integral theorem here? So I can use it here. What I would do is, I have to integrate over this particular upper half. Only upper half I'm saying. I'm not including this. ठीक है, ये सिर्फ एक लाइन का लॉन्ग इंटीग्रल की बात कर रहे हैं इस क्वेश्चन में. ओके, व्हाट यू कैन डू, as Bharat says, what you can do, you can clearly go on and make a complete closed curve. इसको closed curve बना दो. ठीक है, and let's say this closed curve is gamma. So according to Cauchy's integral theorem, fz dz over closed curve would be equal to gamma, but it will be equals to integration over c plus integration over line, but line का integration along this, मतलब समझ पा रहे हो, मतलब ये होगी डायरेक्शन लाइन के इंटीग्रल की, एंड c के along जो इंटीग्रेशन होगा वो it will be in the anti-clockwise direction. Eventually you will get what? Integration over c will be equals to minus of integration over line in this direction. So basically it will give you, it will tell you that integration over c is equivalent to integration over line in this direction. This is what we have done. Understand my point that the Cauchy's integral theorem would only be applicable if you have a closed curve. This is not a closed curve. I have just written upper this. I'm just talking about this. Are you getting my point? ये बात समझ में आई भरत को? है ना? This particular line I'm talking about. That is why I told you that I will have to write some parametric coordinates to these lines, because parametric coordinates to circle is z minus half r e की power iota theta, and z is equal to 1 by 2 rho e की power iota theta I will have to write. Then I will have to vary the rho. Rho will be varying from, I think this will be a very difficult task, because see here theta would be in this fashion. So it will be a slightly difficult thing for me to do right now. So instead of doing all these parametric sort of integral, what I would do, I would prefer going for a principle of deformation of contour. So what it will give me, it will give me that all these integration along this line, along this particular curve, if you do an integration over this particular C, or you do integration over L, it means the same thing, provided while moving, while doing a deformation, I was not encountering any singularity. If at all I encounter singularity, this will not be applicable. This will not be applicable. Okay. So let us see a scenario where it cannot be applicable. Okay, let us see a scenario where it cannot be applicable, and then we'll move ahead. Okay. So try to find this integration. I'm saying try to find me I1, which is integration, I think, over, let's say, I would write C1 dz upon z, and I2, which is integration over C2 dz upon z. Okay. Here C1 and C2, मैं ऐसे लिख देता हूँ, C1 and C2 are upper and lower semicircles. Upper and lower semicircles of the unit circle, mod z equal to 1. And both are traversing in opposite direction, traversing in opposite direction. मतलब अगर C1 clockwise है तो C2 anti clock है, पर C2 अगर clock है तो anti clock है, traversing in opposite directions. So this is not a closed curve in general. ठीक है, opposite direction. My question is, will I1 be equal to I2? Will I1 be equal to I2? So what I'm doing is I'm integrating I1 individually, I'm integrating I2 individually, and I'm just asking you, let's say if I'll draw the curve, देखो ऐसा कुछ, and I'm asking whether I1 and I2 would be equal. So what I will do, I'll do a thing for you. Let's say if I let's say this is my circle. This is my circle, okay? And if I make certain lines over it, okay? अरे यार ये क्यों नहीं आ रहा? Okay, so these are my lines, and I'm asking you that what if I'm saying this is my C1, and let's say I'm moving on the C1 in clockwise direction and along C2 in anti-clockwise direction. Okay, now I'm asking if I integrate over C1 and if I integrate over C2, this will give me an integral I1. Please consider only the upper half, okay, and in this lower half, okay. And if I integrate over C2, I'll get integral I2. I'm asking whether I1 will be equal to I2. So, and this is a unit circle. So it is fairly easy to see that the parametric coordinate on the circle would be equals to e की power iota theta. Okay. Is that understandable? क्योंकि देखो सर्कल के ऊपर कोई भी कोऑर्डिनेट कोई भी पॉइंट कैसे रिप्रेजेंट किया जा सकता है, r e की power iota theta. And you can see that here it is a unit circle. So r is equal to 1. Yes or no? So if I integrate over C1, I will get what? अच्छा, C1 के लिए, because C1 is a, what should I say? Uh, Clockwise orientation. So angle would vary from pi to 0. Okay. So angle would vary from pi to 0. If I'm talking strictly in the sense of principal argument. Okay. Like angles in the principal argument. So like generally हम क्या लेते हैं? थीटा लेते हैं माइनस पाई से पाई के बीच में, याद करो. So यहाँ पे एंगल्स बोलते हैं 0 से पाई, इधर एंगल बोले जाते हैं माइनस पाई से 0. ओके, अगर अलग लोगे तो भी इट विल नॉट मैटर, दिस 0 से 2 पाई भी लोगे तो भी कोई इशू नहीं, बट आई एम जस्ट doing what I have taken. Okay, so when I'm moving from here to here, my angle would change from pi to 0. So I would write my theta varies from pi to 0 in C1. So my integration over C1 fzdz would be equals to what? It will be equals to integration, I think, iota e की power iota theta d theta divided by e की power iota theta. Okay, this is dz upon z. Z की जगह आपको क्या लिखना है? सिंपली आई थिंक मतलब e की power iota theta का डेरिवेटिव करेंगे तो ऐसे ही कुछ आएगा. And this will vary from where to where? This will vary from pi to 0. This gets cancelled, and this will lead you to answer minus pi iota. Okay, and similarly, if you're trying to find what will be the integration over C2, so C2 will give you again fzdz. This will give you an integral from, I think, minus pi to 0 iota e की power iota theta d theta upon e की power iota theta. This gets cancelled, and eventually you're left with the answer pi iota. Okay. Now you would say to me कि यार यहाँ I1 I2 के बराबर नहीं है, बट जैसे मैंने पहले किया था, this particular curve can actually get transformed to this particular curve. दिख रहा है ये? This particular curve can get transformed to this particular curve. Okay, देखो, this particular curve can be transformed to this particular curve, isn't it? So why did principle of deformation of contour fail here? Are you getting my point? See, I told you in principle of deformation of contour that if I integrate over C1 or I integrate over C2, this is one and the same thing, because see, they both can be deformed. I think, see, let's say C2 is being deformed continuously, C1 is being deformed continuously. So isn't it equal to integrating over this along this line? So why I could not deform? Why could I not use this principle of deformation of contours? Any idea? Bharat, any idea? Alpna, any idea? Or Kadambini, if she's understanding what I'm saying, any idea?
Maybe because of the direction.
Maybe not because of the direction, maybe because the function itself becomes non-analytic at z equal to 0. Okay,
Oh
so
yes.
function was, so I told you that if I'm saying that in this region R, my function has some singularity z equal to 0. I cannot, in principle, deform. I have to deform in the, like, we should understand that if I'm using a principle of deformation of contour, one contour can be principally transformed to another contour provided it does not encounter any singularity. But what about z equal to 0? So understand my point. Time and again I'm saying principle of deformation of contour would be applicable if I can transform my, if I can deform my contour to a different contour, provided in the process of deformation I should not encounter any singularity. Okay, are you getting my point? ये चीज समझ में आती है? So I'll write it here. So what should I write? Since 1 upon z is non-analytic at z equal to 0, that is z equal to 0 is an isolated singularity here, is an isolated singularity. It implies that C2 or C1 can be C1 or C2 cannot be transformed to, cannot be transformed to C2. ठीक है, without encountering, without encountering the singularity at z equal to 0. Okay, are you getting my point? So therefore here you cannot apply the principle of deformation of contours. I hope it is clear. Okay, so such questions, such kind of skill may be in examination, because in examination usually people don't ask big questions, like they don't have that freedom to ask big question. Okay, because वहाँ पे फिर तुम्हें, how would you be able to complete or converge to the solution in the right time? So probably these small and very important concept can be very useful to you. So for example, if I go and ask you, if I go on and ask you what will be integration z and dz, and for simplicity I
सर
would say, हाँ बेटा बोलो.
सर यहाँ पे हम स्लिट इंट्रोड्यूस करके अवॉइड नहीं कर सकते सिंगुलैरिटी को?
Again P value problem, slits and all those sort of concept would come if you are having closed curve. Now here direction is an issue that it will very much initially, so this is not a closed curve, so to say. So if you have a slit, if you have a closed curve and I'm trying to say कि वहां integrate करना, then you can introduce a slit and evacuate this kind of singularity.
ओके सर.
Okay, that would do. मतलब वहां पे हम करेंगे भी इनफैक्ट आगे जाके. So that would do. For example, if you say what would be an integration of 1 upon z, uh, if it is a complete circle, then I would say this will be 2 pi iota. Okay, so I would do that, all those things, but understand my point. This is not a closed curve. Okay.
यस.
Okay. Let's say, for example, I'll again go back to us, because I was in the initial question, I was not able to figure out, I was not able to figure out the right sort of parametric coordinates in order to define a semicircle. I'll bring it to your attention a very simple thing. I think this will be a simple thing to say. So for example, if I say just find me an integral of z ki power n dz over a circle centered at origin with mod z equal to 1. Okay, so how to find this kind of integral? So I told you that any point on the circle, I can write e ki power iota theta. I can write it as e ki power iota theta. So what I will get is, I'll get d theta would be equals to iota e ki power iota theta d theta. And this will be e ki power iota theta raised to power n. Yes or no? And integrating over the entire thing would be equivalent to writing integration over 0 to 2 pi. Okay, so this is equivalent to this, isn't it? And eventually I'll end up with e raised to power iota theta, और यहाँ पे लगा देते हैं n plus 1 d theta. Integration over 0 से 2 pi. Always understand this integration will always be 0. कैसे? देखो iota, you write it in I think cos n, जैसे कहते हैं sin form के अंदर, cos n theta d theta plus integration sin n plus 1 theta d theta. And you try to integrate it from 0 to 2 pi. This integration will obviously go to 0, because cos 2 pi is 1 and cos 0 is also 1. And this will also go to 0 because cos का integration sin होता है, sin 2 pi is also 0, and this is also 0. See, if I do this way, or if I just use principle of deformation of contours, so clearly you can see that z is to power n is an analytic function. Are you getting my point? So z raised to power n is an analytic function, and for analytic function, if you are in a simply connected region, you know that there is no such singularity inside. Okay, so this is a simply connected region, that is mod z equal to 1. Also understand that you can apply Cauchy's integral theorem also here, but if you want to apply principle of deformation of contour, so what you can do is, see, this particular entire curve can be shrunk to origin, isn't it, without encountering any sort of singularity. So this will answer would become obviously 0. Okay, so this is the power of, so if I had not this, if I had any sort of region, like if I have here to yahan to I had this freedom of writing the coordinates of the circle in form of some parameters e की power iota theta. Had it not been the case, if I had only any sort of curve, so या तो तुम principle of या तो तुम Cauchy's integral theorem दिखा दो, क्योंकि this is a closed curve also. But if you don't want to do that, see, clearly understand, it will, ये सारा का सारा, if I try to deform, it will succumb to origin. So it will succumb to origin, and eventually your integral will succumb to 0. Are you getting my point? ये चीज समझ में आई?
Yes, sir.
Okay. So if your curve can be distorted to a point, or it can be, like in this case, it can be distorted or deformed to a curve, or probably in this case distorted to a point, it is not a problem, provided you should understand while deformation you should not encounter anything. Okay, so let us move to two standard cases that we did yesterday, and we'll take things there from forward. The first, second thing that you should understand is, for example, if I am in the closed contour, if I am in a closed contour C, if I'm talking about a closed contour C, okay, if I'm talking about the closed contour C, and these are the points, let's say A and B, and if I write this as C1 and this as C2, so this is a closed contour C, and this is C2 and this is C1. So what does principle of deformation of contour say me? If I have to integrate from here to here or here to here, it means the same thing. I can simply go and say that integrate from A to B. Integrate from A to B. Either you go this fashion, or you simply try to deform your C1 to line, C2 to a line, and eventually you'll end up getting deformed to a single line. Are you getting my point? And this particular integration uh, uh, means the same thing. Okay, so kindly understand, or if I use the Cauchy's integral theorem. So if I Cauchy's integral theorem, so I'm saying my FZ is analytic in, you can say, an analytic in region R. Let's say this is your region R, in which you have this closed curve C. This closed curve C contains C2 and then C1. So integration over C, Fz dz would come out to be equals to what? 0. And eventually, what does it mean? It means integration along C1 plus integration along C2 equal to 0. Understand, C2 is in this direction, C1 is in, C2 is in this direction, C1 is in this direction. So these are opposite directions. So this will give you minus integration C2, and this will give you integration over C1 is equal to integration along C2 in the same direction. Okay. So what are you getting? You are getting that whether you integrate along C1 or you integrate along C2, this means one and the same thing. Okay, this means one and the same thing. And basically what you are doing, basically when you are integrating from like C2, you can principally transform your contour to a line. So basically what it means that if I want to integrate, if I want to have a let's say integral from A to B, it hardly matters whether I go from C2 or whether I go from along the line along the curve C1, or whether I go along the line C2, it hardly matters. So this is one of the similar statement that you will find in your conservative vector fields, that if you want to integrate from one point to another, the line integral for a conservative vector field, for potential which derives from a conservative vector field, is independent of path taken. It only depends on initial and the final points. Are you getting my point? ये चीज समझ में आ रही है?
Yes,
That is
sir.
along C1 तुम जा रहे हो तो हो क्या रहा है? Along C1 जा रहे हो तो basically A से लेकर B जा रहे हो. एंड अलोंग C2 जा रहे हो तो मतलब क्या हो रहा है, B से A जा रहे हो. सो चाहे तुम अलोंग C1 गए, चाहे अलोंग तुम C2 गए, बात एक नहीं होगी. एंड इवेंचुअली यू कैन राइट अलोंग C1 इज इक्वल टू अलोंग C2. सो बेसिकली व्हाट डज इट मीन? It means that if you are in a simply connected region, if you are in a simply connected region, and if you want to find a line integral, if you want to find a line integral from point A to B, it will be independent of path, whether you take path C1 or whether you take path C2. Are you getting my point? So should I
Yes, sir.
write it? Should I write it? So if my function is analytic in a region R, so let's say my function is analytic in R, and I have to integrate from Z1 to Z2 fz dz, then this particular integral, this particular line integral would be independent of the path. This is similar thing that you find in your mechanics also. That if I say that my like let's say uh, u vector is a conservative vector field, so I can write it in the grad phi dot dr. याद करो. So if it is a conservative vector field, then I can write it in some potential formulation, grad of something. And this, let's say if I'm moving from R1 to R2, so this will give me phi R2 minus R. So eventually, I find that my integration depends on initial and final point. It does not depend on path taken to reach from R1 to R2. So this is a kind of similar statement. So that is why I want to draw your attention. Okay? So we'll move on to another topic in next class. I hope everything is clear.
So we have one more class.
Yeah, we have one more class.